Welcome to the lecture block Similarity Modeling 1 and 2, Seeing and Hearing in Computers. Today's block is on feature engineering. My name is Horst Eidenberger. In feature engineering, we deal with the old-fashioned signal processing methods that are used and have been used for a long time in order to summarize visual content and audio content in the context of computational perception. That is, clever algorithms employing transformations, employing convolution operations, employing so-called kernels and many other technologies more in order to build a good model of the input media data streams. As we said in the lecture on the setting, which you should have watched before you watch this one, modeling is of paramount importance for actually understanding the contents later in the similarity measurement step, because without it the data load would be too high, way too high, and there would be a high level of redundancy and a low level of information in the data, which is corresponding. So what are the goals of feature engineering today? In the first part of the lecture, I will try to make you understand what the relevance of feature engineering is today. You might be of the opinion that due to deep learning, feature engineering is not required anymore. Why is that? Deep learning means that you use many layers of convolutional functions or of recurrent functions such as the LSTM in order to automatically learn the relevant features from training data. Input data plus labels that tell you to which category a certain input media belongs. That is true and not true at the same time. In the visual area, and in particular in visual object recognition, deep learning has certainly revolutionized our trade. However, in other areas, in large parts of the audio domain, in certain problems of motion analysis in the visual domain, problems of higher semantics understanding, deep learning does today not outperform classic methods. And classic methods, feature engineering methods, very often require significantly less computational power. So if you do, for example, edge computing, meaning that you do the processing maybe on a small embedded computer such as a Raspberry, directly where you need the data, then of course resources matter. Today with cutting-edge hardware, you're usually able to process, if it's a bit more complex in the visual domain on the edge, like 2 to 4 frames per second. If you need more, like in virtual reality applications where it starts to become interesting at 90 or 100 frames per second, then apparently deep learning methods are often not able to provide this sort of performance. And then you can go back to classic feature engineering. Plus, there are plenty of libraries by now. The Open Computer Vision Library is just one of them, librosa for the audio domain. We come to that later. Sorry. That you can readily use out of the box. Furthermore, in this course, of course, you have to employ both methods. If you go for Similarity Modeling 1 and 2, you have to do one classic approach and one deep learning approach so that you can compare both methods and get a feeling for that. And in the event, it is still our motto at TU Wien to teach the students the history of technology as well and to give them comprehensive competence. Only if you have tried feature engineering, you can make a judgment in a certain situation, a certain application scenario, whether it would be helpful or not. Very often it's also used as a pre-processing method. So the first goal is definitely to understand the relevance. The rest of today's lecture is practical or is directly applicable, so you can say. It's both toolboxes, one time for the visual domain, the other time for the audio domain. Today we limit ourselves to features, feature engineering in the temporal domain, so you will never have to use the Fourier transformation. If you're interested in that, there will be a lecture in Similarity Modeling 2, where we deal with integral transformations and the feature engineering methods that are based on them. These are still state-of-the-art, for example, in the audio domain. So these are our educational goals. And now I would say let's jump directly into the topic. And we go back to a slide that we already had when we spoke about the setting of media understanding. There we said that it's a process, media understanding, of modeling data, input data, and measuring similarity. So if the input data is denoted like a database, because it's usually of big size, the first step is the modeling, and that is in the classic world done with feature engineering, thus providing a feature space. We have the feature space when we spoke about similarity, in the block about similarity, and after this block you will have a block on classification where we will speak about it in greater detail, because the feature space is the standardized input for the classification step. And that eventually provides you your semantic knowledge, your label. Okay, let's go to one or two examples. Consider you have to do a feature recognition algorithm for your grandmother. Then the media input database would be a face database. Feature engineering would include, for example, methods from texture recognition and shape recognition. We come to that in a minute. The feature vector would certainly have 300, 400, maybe 500 dimensions. And the class labels, the classification might be a support vector machine, ending up in a class label saying that this is a picture of your grandmother or not. Or, so let's put it like this, which would be a predicate form, or it might be a class label saying that this is an old lady with gray hair and the similarity to your grandmother is this and that. So label can mean a lot of things. It might be a predicate, it might also be a quantity, it might be a cardinal number, something in between. Okay, good. That was one example. If you have to recognize Kermit the Frog, such as in the lab course sometimes, then the media input database would be videos of the Muppet Show, of course. Feature engineering could, for example, be based on color features, because Kermit the Frog has this distinct green color, and of course the lighting in the Muppet Show is very good, so this green is almost ever recognizable. The feature vector and classification could be a simple decision tree. If green is between a value of a lower threshold and a higher threshold, then label a frame as containing Kermit the Frog. Does label contain Kermit the Frog is another predicate. Okay, so these would be two examples of the process. Now, what does feature engineering practically mean? Practically, it means dealing with these signal forms that we already discussed about in earlier lectures. How do we do that? I'm still not happy with that. Okay. How do we do that? We have to find the points in the feature space that are of relevance. Relevant points, as we said in the visual signal, here in an image signal, if you remember, this is from a screenshot of a newscast of MSNBC. The relevant points, I said, are those where the color or the brightness changes significantly, where we have a so-called edge, a transition between dark and light. In the image domain, color is normally of relatively limited semantic significance. Why is that? Colors can be changed. Kermit would still be recognizable if he wasn't green but red, for example, or blue, because of his shape, its shape. Okay, so we are not so much interested in changes in color, but in changes in brightness. Of course, brightness is affected by colors. Some colors contribute more to brightness, such as red, than others, such as blue. The blue channel is quite irrelevant, only 10% contribution to the brightness value. So in the visual domain, it's quite clear what we are looking for. We are looking for such transitions. I will show you a couple of methods that explain you how you can actually find them. And they are called, as we said, edges, edge information, edges, and sometimes also corners. Okay, in the audio domain, we are looking for something different. We are looking, for example, for the amplitude, for the sheer loudness of a signal. We might also be interested in the reappearance of certain patterns because they might express a certain rhythm, which is, for example, important in music. We might be interested in recognizing the fundamental frequency. So how often does the signal change the membrane from minus to plus and back? All these information can easily be extracted in the time domain. When it comes to visual signal, we might also consider the information that lies between two frames. Video, as you should know, is a sequence of individual pictures that might be encoded with motion vectors and macro blocks and so on in a very clever way, so to compress the data rate significantly. However, in the end, they are decoded into a sequence of images. If we are following one object from one frame to the next, maybe here going from right to left over 3 frames, we also use convolution methods, and we will also talk about that today, and that would be motion analysis. Okay, so furthermore we have color as an indicator. All that information lies in the signal, and that's why the methods used in feature engineering mostly come from the area of signal processing. Good. Just a reminder, all those figures that I'm using here in the lecture videos can be found in the original form as PDFs in online in the TU forum, in the TU Wien e-learning forum. Furthermore, the scans of the images that I'm painting here can also be found together with the lecture videos. The link is provided in the TU Information Systems, TIS, as well as at the end of this video and all other videos. And if you have any problems, any questions, post them in the forum or get in contact with your lecturer. Also discuss it, of course, with your colleagues in the groups. Okay. Good. So now, let's start off with a few nice little features. Let's start with the visual domain because it is very simple to understand. Consider a certain image. Let's put it in the middle, but not too big. And we try to recognize Kermit the Frog. Something like this. I'm very not good at painting. Okay, so how can we do that? One first approach is obviously we can try to identify Kermit by the colors of his coating. Kermit is a hand puppet. His color is green and it's very furry. So it got both color aspects and texture. Texture properties describe the surface of a visual object or any tangible object, of course, in reality. But for us, we can only have the visual aspect, apparently, in our recognition system. Okay, now the question is, how can we describe color? Spontaneously, and very often in the old days, students would submit that already. People would say, yeah, why not use the RGB values? What is RGB? It's red, green, and blue. It is a description of each pixel in the image, each usually given with 1 byte. So 3 bytes describe a multitude of different colors. The amount of red, green, and blue allows you to describe all colors that we have in the spectrum according to the so-called 3 stimuli theory that you should have heard of in the multimedia courses in the bachelor program. Okay, RGB is a nice color model for encoding and for compression, as the basis for compression. Itself, of course, it doesn't provide any compression. However, it is not suitable for our problem of recognizing the green of Kermit the Frog, because the green that we have in the RGB is a pure green. It is significantly different from the code of Kermit. What we need is a color model where we don't have 3 basic colors, a 3-dimension in a vector space. We need a description where we can actually have a U value that tells us something about the color, and only secondarily about the level of brightness or the level of saturation that we have in the image. Brightness meaning dark or light, saturation meaning presence or absence of a color. Even if Kermit is green, that green is not as present as the full green in the RGB value. So my recommendation for you is, if you go for a color feature, which is fair enough for Similarity Modeling 1, and use a simple classification method to find Kermit, which has proven quite successful in earlier years, don't go for RGB values. That is not the right approach, but employ a color transformation. For example, to the U saturation value color model. You find also these figures in the PDFs in the e-learning platform. What does U saturation value look like? It is a color model tailor-made for computer vision applications. It converts the 3-dimensional RGBs in another 3-dimensional space, so there is no loss of information. All colors in the RGB space also exist in U saturation value, and of course you can at all times convert back. If you use a library like the OpenCV library, which is allowed of course in the core, in the lab, you have very convenient conversion function. You just open or capture an image, convert it directly from one space to the other, and become able to focus only on the U value. Yeah. The description here is a bit different. As you can see, the U value defines the color. It is the rotating dimension, whereas the value color defines the absence, or not the absence, but the brightness, and the saturation, the presence and absence of a color. In the middle you have the white spot, meaning that there is no color present, and on the outside you have the full color. So you will probably go for, if you go for Kermit, for saturation close to the maximum. You will pick the sector with the green values. How can you do that? By masking out everything else, for example. And you will go for probably medium values for the value component. And that is very helpful. Another very helpful color model that is also available in most computer vision libraries is the XYZ of C, also known as the color sail, where colors are not just represented by 3 components, X, Y, and Z, of course, but they are represented in a way that corresponds to the way our perception actually works. So there are, in short, more green tones than, for example, yellow tones, because the human being with our vision system can distinguish more forms of green, more shades of green than, for example, shades of yellow. Last color model that I want to show you is the Ycrcb, because it is important in broadcasting. That gives you three components: a luminance component, which is brightness, a sheer brightness, usually built by taking like 60% from the R value plus I think 30% of the green value and only 10%, as I mentioned before, of the blue value. And that is exactly the luminance values that are used in this graph of the images. This is a very technical format. Luminance, maybe I should write it here, is not itself a color value. Therefore, it's augmented by a different signal subtracting from the white channel the red channel and subtracting from the white channel the blue channel, thus introducing a certain level of redundancy. And why do we do that? Because this is a broadcasting format. So if we have a loss over the line, over the cable, then we might be able to reconstruct certain parts of the signal. And even if we lose both color channels, we still have the luminance value, so we can show the full picture information just without color, which is in particular, or was in the old days, acceptable when one had a transmission problem. Okay, so these are 4 color models. More do exist. As you see, you have hue, saturation, and lightness here, and many others more do exist. The important thing is it's usually 3 components, because that allows to show the full spectrum. RGB is uniformly distributed over the 3 channels, so very nice for image encoding and very simple, but not made for semantic enrichment or understanding of something like, is there a Kermit in the picture? Hue saturation value is much better for that. Conversion is very simple, you don't have to do it by hand. For broadcasting applications, Ycrcb is a state-of-the-art still, I would say. And of course, there is also a psychophysical format with the XYZ model. Okay. Good. So, using that color model is not the solution yet, no? Because if you convert the image from this domain, from the RGB domain to the hue saturation value domain, you still haven't done any form of compression, any form of modeling. If you want to do that, you have essentially 2 options, classic options. And one is to compute a color histogram, and the other one is to compute the so-called dominant color. The dominant color is the color that shows the most pixels in the image. There is an infinite number of different ways how this is played. Many approaches, for example, go for not the entire images, but assume to have the important information in the image somewhere in the center, whereas other parts, such as the corners, are neglected, are not used at all. So you count only the pixels with colors in the center of the image and use the dominant color. Another approach is to look explicitly for the biggest blobs. That is a blob. So a continuous region with the same color, more or less same color. These are 2 approaches of dominant colors that you can use. There are convenient libraries of the so-called MPEG-7 standard that provide you a dominant color description. You don't have to compute or develop an algorithm by yourself, but you can employ this library. There are various implementations, and some of them are linked in our forum, but it's also easy to find one by doing a simple Google search. That was the MPEG-7 standard for the description of multimedia content. Likewise, color histograms are in the MPEG-7 standard. A color histogram means that we take the different hue values and just count the number of pixels present, thus forming a histogram, which is obviously a vector, and that vector can be directly converted to a feature space. So color description is very simple. It might prove very effective in your case. It can be done directly in the so-called time domain. You don't have to do any integral transformation. And in particular for finding Kermit the Frog, I think such an approach would be a good starting point to get a feeling for what feature engineering can do, to use a simple classifier. It's a good entry point, I believe. Another idea is to go for texture, so for surface properties. How would you do that? Surface properties exist also in multiple ways, in multiple forms, sorry. The most important are patterns of directionality, so whether pixels are all showing in the same direction. Then, of course, rhythm patterns. So if the same texture appears again in multiple positions in the image, like the checkerboard pattern. So directionality, we said. And rhythm is another important aspect. And the third one is coarseness. Coarseness is the difference between a checkerboard pattern with 4x4 white and black squares or 16x16. The 4x4 is coarser than the 16x16 apparently. And that might also contain information. For example, the fur of Kermit the Frog has distinct textures with lighter elements and darker elements, and those might be identifiable through texture features. Practically, all three can again be taken from the MPEG-7 standard. So you don't have to implement anything by yourself, but method-wise, it works as follows. What you do is, for example, to identify the rhythm is to take one patch, a so-called macro block, and look in the environment of this, in the neighborhood of this patch, like for example in the circular environment. Look whether the same pattern appears again and again and again. So how would you do that? The simplest way is so-called autocorrelation. In autocorrelation, you take the original patch, let's denote it as P, and go through all of the neighbors. That is apparently the environment of the original patch is a loop, and compute the convolution of this neighborhood with all the neighbors n. Okay, so that means n2, n1, n3. You loop over this aspect, and then you take, for example, a certain threshold value. If that is being exceeded, you say that the pattern P repeats itself in nx, and therefore we have a rhythm of reappearing patterns with an interval of, I don't know, 100 pixels. This is our first application, which I promised you, of convolution operators. Implementations exist both for positive convolution, but also for negative convolution. Negative convolution is the more popular one. You should have watched the video on similarity already. And therefore, you should be aware that this is actually a distance measure, which can be converted into a similarity function. And therefore, what we do in autocorrelation is we take one part of the image and compare its similarity to neighbors. Since we compare part of an object with other parts of an object, we stay within that object, and therefore it's called autocorrelation. Correlation is just another word for similarity measurement. Similarity is correlation is convolution over normed vectors, and therefore a typical similarity operation. Okay. Of course, the greater than is only valid if we had stayed with the positive convolution. If we go for the negative one, then of course the distance, the difference has to be below the threshold. Okay, so this is a first application in rhythm detection for similarity measures. Normally you would learn that in signal processing that we employ the L2 norm because we have always done it that way. They would not explain to you why it is. You know with your knowledge from the other lecture block that this is a similarity measurement operation. So we are looking for similar patterns in neighborhoods. Also, the idea of using a neighborhood is very typical for feature engineering. Okay, how do you implement directionality? Maybe based on the rhythm features. There are of course different ways to do that. And if you stay with the rhythm feature, then you can compute all those values of the convolution operation and maybe compute statistical moments. A mean, a standard deviation, and whatever moment you want to use. Most relevant one, of course, for directionality is the standard deviation, meaning that if it is low, then apparently all of the patches are investigated are pointing into the same direction. The second relevant is the mean value, because the mean value then tells us, is it a significant amount by which they are pointing in the same direction? Or is the correlation between the two, the similarity between the two, actually very low? So only if the mean is high, beyond a certain threshold, and the standard deviation is very low, below a certain threshold, we have a clear pattern of directionality. Now, how do you compute coarseness? Coarseness can easily be computed by doing the same, for example, rhythm detection, but on different image sizes. The original size may be half the size, which can again easily be computed by OpenCV. If the pattern remains the same, despite reducing the size of the images, then apparently there is not more information in the original image than in the compressed image. And therefore you conclude that this is a rather coarse image. If it changes the directionality pattern, for example, also the rhythm pattern, any feature can be used. This is an example of using a feature on a feature. So it's a cascade of features. Then apparently the image information is not coarse. Every pixel then contains information in itself. By compressing the image, making it smaller, we are losing information. If that is not the case, as I said before, we have a coarse image. Okay, these are two ways of describing image information. As I told you before, both texture features and color features are available in all vision libraries that I'm aware of, simply because they are classic methods. When I started my way in science with the PhD in 1996. There was already a first image understanding system by the IBM Corporation called Cubic that could do a simple form of texture recognition and a very good form of description of colors by color histograms. So these methods are very old. Good. A third thing that you can apply is edge information, or as we sometimes call it, shape information. Sometimes we also say corner information, because in the end we are not so much interested in where a certain edge goes along, but we are more interested in where it starts and where it ends and what form of curvature it has. That means we can again compress the amount of information that we have. So essentially, what does it mean? It means identifying the boundary between Kermit and, in this case, the background. So just like the blob detection, but for a different purpose, we are interested here in the green foreground and the purple background in this case. That is a typical edge, such as the edges that I showed you in this graph. Maybe purple is very dark, is shown here, and the green of Kermit is rather light. Then the transition from the background, from the dark background to the light foreground happens exactly here. Okay? As we said, that is the local information we are interested in. Just a reminder again, we will come to audio features after this little block. There's a fundamental difference between the two. Visual information means we are interested in localities. We are interested in local information. Hardly ever are we interested in local information when it comes to sound, because sound is usually a composite of different sources, of different frequencies, of overtone structures, of timbre, and so on. That means we are interested in a holistic signal, okay? But that's just as a side note. Well, how do you compute edge information? The way you compute edge information is by so-called cross-correlation. And what does cross-correlation mean? Let's paint another frame. Cross-correlation means to take a frame and over all locations in that frame, maybe all non-bordering ones to make it more convenient for us, and so on. Do a convolution with a given function. That given function might be as simple as that little matrix. It might also be a bit more complex. Or it might look like this. Okay, and that function we call a kernel. So this is a kernel. Magic stuff. What does it mean? It is actually the idea that is also implemented in deep convolutional neural networks with a little difference. So we take the original image information, and over all non-border points, we fold with the convolution operation a simple operator. What does it mean? We are apparently looking for regions in the image that are similar, or if we employ negative convolution, which is the more common form, that are dissimilar to that pattern. But normally we are interested in similarity, so the negative convolution is changed by some form of generalization. The simple form of generalization, of course, is to change just the direction of the relation with the threshold. Okay, but that I think is obvious. So if I compute the similarity of a 2 by 2 neighborhood in an image to an operator that looks like this, what do I get? I get something that looks visually like this, which is an edge information. An edge information which is, for example, a transition from purple or dark to green or light. Let's assume we always work on the so-called luminance channel that we had before in the color models. Then we are rid of the two other channels. We can apply the transformation in this case directly. Otherwise, we would need 2 or 3 submatrices for the different color channels. But it's more common and more easily done if we operate directly on the luminance without losing any visual information, except the color, which is usually semantically not loaded. Kermit is an exception here, because Kermit is the toy example for the lab course. So, if we find such an edge, we can then classify it as the distinction between maybe a darker background and here starting a lighter foreground, for example. So that gives us information of a diagonal edge. This is one of the operators coming again from MPEG-7 in the so-called edge histogram there. That is one form of shape description. Feel free to use it on Kermit or on the identification of Waldorf and Staedtler. I think with Kermit you're good if you go for color information. If you have to recognize Waldorf and Staedtler, for example, the 2 elder gentlemen on the balcony in the theater, then probably color will not help you as much because they have about the same color as the chairs they are sitting on. So it's probably necessary to go for something more complex, which might be a texture feature or, of course, a shape feature, shape description. So this is a very simple 2 by 2 operator. That one is another one. It's very famous. It's the Laplace operator. The Laplace operator looks for areas that are dark on the outside and light on the inside, or the other way around if we employ the absolute value, which is done most of the time. So we do the convolution operation and then we take the absolute value. Then it recognizes both things that look like this, but they also recognize something that looks like this with the dark center and the light outer region. The third one is the so-called vertical Sobel operator. There is one transposed form that is the horizontal, and that one apparently is also an edge operator. That means it recognizes a transition from light to dark, however, in a more robust way than the small MPEG-7 operator does. MPEG-7 strategy is to kill the problem with performance, with many edges, whereas the Sobel operator relies on good edges. Okay, all these are classics. The Laplace operator dates back to the 1960s to the first robotic application. So does the Sobel operator. MPEG-7 was defined in the late 1990s and is also a classic by now. Good. So what can you do is you employ such an operator, get the edge information and use it directly as a feature, but more oftenly compute more complex features based on this operator. MPEG-7 again provides a solution. What is the solution is they count the number of such edges. They don't say, well, we compute an image that looks like this, but we count the number of diagonal edges. We count the number of vertical edges, of horizontal ones, and then create a histogram like with the colors, but only for these counts of edges, and that can be nicely used as a feature. Of course, you are always free to employ it not on the entire image, but maybe on 3 by 2 subregions, neighborhoods, if you like. The essential operation, however, stays the same. It is apparently the similarity operation. So we are measuring similarity between the image information and a prepared kernel function that stays the same for all localities. Therefore, it's not autocorrelation, but cross-correlation, because we're measuring similarity for covariance over normed vectors from a source to something static, and that is called cross-correlation. If you stumble over that term, you should know what it means now. Okay, then the last thing that I want to paint on this picture is a simple thing for the for the recognition of camera movement, foreground and background. Maybe let's start with the foreground background thing. What you do here very often is that you take different regions, a center region, and maybe outer regions, and employ, for example, a coarseness operator on them. And if the coarseness is high on the outside and low in the center, then, so goes the assumption, the outside is apparently background and the center is the foreground. Why that? Because usually the less coarse the image content is, the more it is in the focus of the recording system. Well, not usually, but that's a tautology, that's how it should be. Okay. So wherever you find a region, and you can use different region templates for that, that has a finer granularity of the pixels, less coarseness, you assume that there is the foreground. In other areas, there is the background. The last thing on that is, let's reflect a little bit on it. Distinguishing the foreground from the background in an image is a semantically highly loaded task. It's not simple. Normally, for human beings to distinguish the foreground from the background, we have to understand what the scene is actually showing. The implementation with such simple feature as coarseness, which is completely unintelligent, bases on an assumption, on an hypothesis, that, of course, the recorder has taken care that the foreground is shown in the greatest possible detail, whereas the background is shown in a coarser Gaussian blurred form, for example. That assumption is true most of the time, or almost ever, when it comes to image information, but also to quality video recordings, and therefore we can make use of it. And thus we end up with a simple feature engineering method that runs very fastly and very stably. Again, you have such an operator in the OpenCV, which I personally love to use because they're really stable, very, very stable, if they give them a bit of training opportunity. So you have a very simple method, a very quick method that achieves a high level of semantics already. That is, to remind you, one of the reasons, or the major reason, why we are actually doing this, this feature engineering step in the similarity modeling lectures, because some of these methods, almost all of them that are presented, are very, very valuable for your practical work. Don't discard them just because deep learning has the top-notch performance for certain object recognition tasks. Very often it's not about sophisticated object recognition, it's about simpler vision tasks. And then you're better off and cheaper off with this form of implementation. And it should be one USP of this lecture, to give you a first feeling, a certain idea, what you can also do, what alternatives you have to just kill everything with deep learning. Okay, so much for the static image features. Now we go to the audio domain, and then in the last part we return to the visual domain and go for motion features, optical flow features. Okay. Last reminder before I flip the pages. We already had 1, 2, 3 applications of convolution operations. Hard to understand with a classic introduction into signal processing, absolutely straightforward once you have understood that these distance operators are matter-of-fact similarity operations. So we're looking for a pattern that looks like this in this. Okay. So let's go for the audio domain. As we said, when we looked at the different forms of signals, audio is a holistic signal. That means we can never assume, or very seldom assume, something from an individual sample, from a group of samples. The vast majority of the features requires you to do a frequency analysis. Therefore, in particular, the Fourier transformation is of paramount importance. However, we don't do integral transforms such as Fourier transformation today. That is a separate lecture block that only comes in Similarity Modeling 2 if you are interested in this advanced topic. However, there is a number of simple features, just as loudness, fundamental frequency, and rhythm, that can still be used also in our context, and those are the ones we are going to discuss now. Okay. Very relevant feature for young people. In particular for young people, is loudness, amplitude in a signal, comparing this segment to a lower segment. Okay, so how do we compute loudness? By a very, very simple form of autocorrelation. Later I will explain you why it is relevant. That autocorrelation simply takes a frame, so a part of an image, maybe with varying size, but most oftenly with the same size. Just n samples, for example. Yeah. One frame might be something between, I've seen over the years, as short as 20 milliseconds, whatever that means. Of course, that depends on the sampling rate, and it might go up to 1 second. 1 second is, I think, the maximum that I've ever seen. 20 milliseconds, typically in speech recognition, and sometimes 1 second in environmental sound. These are two major applications. The third one would be somewhere in the middle between the two, would be music recognition. Music recognition ranges from genre estimation over identifying certain musical instruments, transforming from one voice to another voice, extracting the speech information in content, and so on. So there are many applications. Speech recognition, I think, is obvious. Environmental sound recognition is about, for example, recognizing the sound of a car. Okay, so 20 milliseconds, of course, means something different if we have a sampling of 8 kilohertz than if we have 48,000 hertz, 48 kilohertz. The latter being high quality recording that contains everything that humans can hear. The first one being what is, for example, used over telephone lines, and then the old GSM protocol over mobile phones. Okay, so the first thing that you do is you create these frames, and that is something that happens in almost all audio features, or let's put it simple, actually in all audio features that I'm aware of that are of practical relevance. Okay, that framing is, in our case, a hard cut. We are not employing some method that would smooth the corners. Such smoothing methods often have a Gaussian shape, like the Hemming window and the Henning, very similar but different. But we assume just such a rectangular shape for the framing. We come back to the framing methods, by the way, to the weighting methods, when we speak about the Fourier transformation and its artifacts. Okay, once you have employed that framing thing, what you do next is you do a simple form, I said, of autocorrelation. You compute the so-called root mean square, and that is simply to sum over the individual samples of your frame, square them out, compute their mean, and take the square root, as defined, for example, in the ISO 226 norm for loudness computation. Okay, with the root mean square value, you already have an information of the signal, meaning the amplitudes, independent of their direction, of the membrane in the loudspeaker or in the microphone. Okay, that is a very helpful feature if you use it as a sequence in order to distinguish different types of music. For example, if you think of classical music, you will have a very high standard deviation of the root mean square. If you think of, for example, heavy metal music, the same standard deviation will be rather small because it's all loud. In classic music, you have components that are very loud, and most of the time in a mid-range, and sometimes they're very low. If you think, for example, of the symphonies of Haydn. So that is already a simple form of distinguishing one media type, one media content from the other, by simply going for a statistical moment, in this case, of the root mean square value. Why is it autocorrelation? Because you correlate every sample with itself. So the simplest form of a negative convolution of the sample with itself. Okay, root mean square is used in many applications. You can also use it for recognizing Kermit. Kermit has a typical pattern similar to my own pattern, that he starts with a big announcement, very loud, and then starts mumbling and then becomes lower and lower before he gives another big announcement. And that, of course, is a pattern of high loudness followed by decreasing loudness, lower loudness, and high loudness again. Okay. A second thing that you can use is a feature for the fundamental frequency. The fundamental frequency can be computed with a very simple algorithm. You just take all the points where the signal crosses the zero line. The more you have, the higher apparently your fundamental frequency in the signal is. This is straightforwardly referred to as the zero crossings rate. And still used in many applications today because it is highly effective, and it is also said that the zero crossing rate for many applications corresponds to the most famous audio feature, the first coefficient of the mel frequency substral coefficient. That is not something you have to understand. Now we come back to that if you're interested in the spectral features, in the spectral transformation in similarity modeling too. However, the zero crossings rate is also very helpful for many applications. It allows you, for example, to distinguish different forms of sources. With speech, we are never able to create the same zero crossings rate than with music. So if you have, for example, an algorithm that analyzes radio broadcasts, then already using the zero crossings rate for windows of, let's say, 500 milliseconds allows you to distinguish very precisely between those segments where the DJ says something or where she plays music or a jingle or whatsoever. So this is a very simple method of counting in a for loop over the elements of the signal, or doing some vector operation if you have a more sophisticated environment such as Python NumPy, to be able to extract highly loaded semantics, distinguishing music from human speech. Quite semantic. Okay, the third element that I would like to mention is rhythm detection. We already had a visual rhythm feature in the form of texture recognition, and here we have an audio rhythm feature for discussing what we really denote as rhythm also in everyday life, the repetitiveness of patterns. Let's put it up here because I don't need that space anymore for later on. Rhythm means that maybe we have a pattern like this. That stays more or less the same. Let's paint the Hull curve. Looks like this. Okay. So how do we detect this apparent rhythm? First of all, we need the right window size, and secondly, we need a method for comparison, for comparing one window to the other. How do we do that? This, by the way, of course, is the time domain, and this is the amplitude, such as here and here. Amplitude, time, the samples. So how do we do that? How do we get that? Well, we cannot guess the right window size, so we apparently have to loop over the frame size from a minimum to a maximum, maybe 220 to 500 milliseconds in steps of, I don't know, 20 milliseconds whatsoever. Then pick the first frame. First things first, why not take this one? And then do, you should already know it by now, autocorrelation with the neighbors. So you compute of your frame F1, F2, F3, F1 autocorrelation, typically done with negative convolution because it's a signal processing feature, with Fn bigger than 1. And what do you do in the last step? You compute moments. And that means for example, standard deviation. If that one is smaller than a threshold, then apparently you have a rhythm pattern. Okay, so let's go through it again because it has been a bit much. We are interested in identifying this pattern in the audio signal. We don't know that it's there. We are blind. The feature is very simple. But if there is a rhythm pattern, we can find it somehow. What we do is we loop over different interval sizes. We pick a reference in the second step. Once we have picked it, we do autocorrelation. That means element-wise comparison, this with this, this with this, this with this, and so on. And since this is a distance or similarity operation, if you use a generalization function by turning, for example, a relation sign, then we measure the similarity of the reference frame to the others. Therefore, it is autocorrelation. It is not cross-correlation, it's autocorrelation because the pattern that we are looking for is in the signal itself. And we are acting blindly with the recipe in order to make us see, so to say, or hear in that particular context. And if we then find that, for example, the standard deviation is below a threshold, and maybe to make it sharper, the mean is beyond the threshold, so it is something relevant that we found. It's not just an arbitrary level of autocorrelation, but it's a significant one, and it is constant over maybe 2 or 3 seconds or even longer. Then we can assume, hey, we got a rhythm pattern here, and it is described by this window with this length. And that could then be, for example, the feature that we use in the audio domain. Okay, with that we can also compute patterns such as the attack, decay, sustain, release model that assumes that every sound has a time where it becomes louder, then it will decay, it will have a certain sustain, like in a bell, and eventually you will release it again. Okay, that is one of the audio features, again from MPEG 7, which is eventually based on rhythm detection, attack, decay, sustain, release. So these features can can be used like the simple motion features for audio analysis. Kermit the Frog has a distinct voice. He has a very high fundamental frequency, so you can use the zero crossings rate in order to single it out. It is not as high as Miss Piggy's, but it is much higher than, for example, the one of Rolf and Fozzie Bear and so on. So you can single him out by that. You can distinguish speech signals from music signals by rhythm detection. Speech has less rhythm. You can try to find Kermit's particular attack pattern, and you can also go for this pattern in the loudness scheme by looking for his loud introductions and then his quick decay that he has in his voice. All these features are available in the MPEG 7 library, in the LibRosa library, and in many other convenient Python libraries that you can use in your project. So you don't have to implement anything by yourself. Good. That brings us to the last part of our lecture today, which is motion. And when it comes to motion, we are for the first time dealing with multiple frames in the visual information. So far, we always had single frames. So this is at time t1, time t2, time t3, and so on. And one frame follows the other. We don't care about compression aspects. that is dealt with by the system, by your operating system. So you assume that you already have the RGB frames and you can easily compute them to other types of color models. So how do you detect motion? And the good news is, of course, and there's only good news in this case, that motion can easily be detected by cross-correlation. It's usually referred to as cross-correlation, even though it's rather, in my opinion, a case of autocorrelation. Because you do something very similar to what we did when we spoke about the texture features. You pick regions. Maybe every non-bordering point, or maybe non-overlapping windows, such as here in my example. That doesn't make much difference. And you look in a neighborhood whether you find this pattern again. The twist is you don't look in the same frame, but you look in the next frame. So taking this image P, you look for candidate region 1, candidate region 2, candidate region 3, and so on. These might, of course, and most of the time are overlapping. You might look for every region within a certain diameter of the center of P. So for this one, for example, you would look here, for example. Okay? But the important thing is you don't look in the same frame, but in the next frame. And therefore, science has decided to call it an act of cross-correlation because it's not in the direct same image, but it's in the next image. But if you consider as a multimedia person that to be one media object and highly redundant between the frames, of course, because there's usually not much change, then it would also be just to call it autocorrelation. So how do you do it? Apparently with the same method that we already know, by using some convolution for the candidates that we have. If that exceeds a threshold, as always, then we assume that that part of the frame, that region of interest, moved to a different location. Well, 1 is not very much, so you aggregate and compute moments. That means you take the mean, standard deviation, whatever you want in terms of moments of the correlation operation, and therefore define a so-called optical flow. That is the sum of all these vectors, going from one frame to the next. If they all have the same mean, and the mean is high, then obviously there's a lot of movement between the frames. If the standard deviation is very low, then there's the same movement. If the direction of the movement has a small standard deviation, we cannot just go for the value, but also the direction, then apparently the movement is in the same direction. With that, you can compute something like camera movement. If all motion vectors go in this direction between two frames, okay, I'll stop here, then apparently the camera went into the other direction, which is also semantically loaded information. Because otherwise not all pixels would shift in the same direction. So camera movement is something that you can use optical flow for. You can use it for the so-called motion activity, which is another MPEG-7 feature, which gives you a general information with mean and standard deviation of what is happening if there's a lot of action. Which allows you to distinguish action movies, for example, from romance movies, which is also semantically highly loaded. And generally, the optical flow is a very good summary of all sorts of video information. It's usually very recommendable to use it for the recognition of visual events. And one particular form is the Lucas Canade by two professors. Optical flow that is, for example, implemented in OpenCV. You will recognize that it is very slow because before we compute the moments in Lucas Canade, you do a linear regression, which is costly in terms of computation power and computation time. However, it creates a very smooth and very expressive optical flow. And that is something that is still unbeaten by today's deep networks. I'm not aware of a convolutional network that would be able to compute features for video that are as qualitatively high as those by Lucas Canade optical flow. And we still employ it in applications of, for example, computer surveillance and also event recognition in forensic applications. So that's everything that needs to be said about motion. It is, again, an act of correlation, whether you call it auto or cross. Therefore, somewhere you have to have the convolution operator. You have the usual suspects, some reference, some candidate, some threshold, some greater than, in this case, for positive convolution, some generalization method, and the convolution operator. And from that, you derive semantics. There is movement. That movement must mean that it is an action movie, for example, might be. You can use the motion features, for example, to distinguish Piggy from other Muppets. She has a certain way of moving, of turning her head, for example, very quick movement, and I'm optimistic that with that it should be possible to actually distinguish her from other Muppets and other elements of the scene. So, to summarize, we have learned today about a lot of different features, methods for the summarization of media content, old-fashioned feature engineering, helpful for you in order to have a complete toolbox, a complete set of actions that you can take. Feature engineering methods have been developed over decades. They are quite sophisticated, use as little resources as possible, and sometimes, if you know the context, can reach a surprisingly high level of semantic knowledge. I hope I've shown that. Don't give up on them just because deep networks are better in certain applications. There are many applications where feature engineering is still the best choice and will remain the best choice for robotics applications and edge computing and many others more, because we simply don't need the sophistication of deep networks or don't have the expensive ground truth with hundreds of thousands of example images, for example. Okay, you have a little toolbox of visual methods, all of them time-based, color, texture, shape, motion. That should suffice. All of them are implemented in the most common libraries. Therefore, you don't have to implement anything by yourself, but you just use it in your Jupyter notebook, for example. The same is true for the audio domain, where you can now deal with loudness as well as rhythm, fundamental frequency, which are all very important features. I hope you enjoyed the video. Once again, if you have any questions, post them in the forum, discuss the topics with your colleagues in your group. And the link to the forum is, as always, given at the end of the lecture, and it can also be found in the TU information system. I hope you enjoyed the lecture, and yeah, you have to use the methods in your lab course, and there you will see that they actually perform very well. Thank you.